Hello, everyone. We have... Oh, I've got some feedback here. Hold on. I need to... Yeah, got to remove that. Okay. My bad with that. So we have a guest star with us today. We have Toon Daelman from the Parsica project. And can you tell us a little bit about the Parsica project?
Sure. So Parsica is a parser combinator library. There have been a few of those in the PHP world in the past. So yeah, I should start by telling what's different, or maybe I'll start telling what parser combinator library means. Basically, it is a way of writing parsers where you write a very small parser, for instance, a parser that knows how to parse a specific character, and then you combine multiple of those smaller parsers into a bigger parser that can, for instance, parse an XML or a JSON file or any kind of parsable document or input, and parse that into um, a data structure that's either the outcome that you want, or it's a tree, like an abstract syntax tree in the structure that you defined for that kind of document. And so that's what Parsica is. Now, we started this with Matthias Verhaas and myself in our spare time, and both of us are Haskell enthusiasts in our spare time. And so we looked at the different packages that are available in Haskell for this kind of parsers. And the cool thing is that some of them provide expression parsers. And that means that you can parse a complete expression language by just defining a few properties of your expression language. For instance, you can define simple arithmetic, plus, minus, etc., with rules about the operators that you can use in that kind of expression language. And then the parser itself will be built completely automatically by our package using combinators inside of Parsica. So that's a feature that the other parser combinator libraries in PHP don't have. So yeah, we're actually pretty proud of that one. um, but there's also a reason why we're here, and that reason is that parser combinators like this, and definitely how we implement it, are almost always slower than the traditional way of implementing parsers. Um, and yeah, we want to find out more about that. So we have a few performance issues. Basically, the normal JSON parser that we implemented is already quite slow for smaller JSON files. So yeah, might be interesting to see what we can find out about that. I hope that's good as an introduction.
Yeah, I think that's great. I think that we'll be able to do a pretty decent job of looking at some of these things and seeing, at least, from a high level, what sort of issues we have that we can look at. So of course, today is an awesome day with lots of issues with GitHub and stuff. So who knows what we're actually going to be able to do as far as like the source code is concerned, if we have to actually look at GitHub or things like that. So I'm going to go ahead and see if I'm going to put us back in private mode for a second. So I was trying to make sure that I had everything set up and ready to go. And of course, everything went a little slower than expected. So I want to get a little bit of stuff here installed, and then we'll be able to jump right in. Let's see. So yeah, can you tell us a little bit about the JSON parser? It looked like there was a benchmark available.
Yeah. So what we did is we went to the JSON schema site. There's like a spec site for
Mm-hmm.
JSON, and they actually have a pretty nice flow diagram, like where they show you how a valid JSON parser should behave. And basically, that whole flow diagram is implemented in Parsica as a demo parser, um, using the combinators available in Parsica.
Okay.
So what we then did is try to give it like a simple JSON input and see what we could get out of it. So we parse it to the standard PHP associative array, just like the default JSON parser in PHP does. So that means we can benchmark it against that JSON decode parser in PHP itself. And then we also benchmarked it against the against another JSON parser written in PHP, which uses a more traditional way of parsing JSON by just going at it one character at a time and using a state machine basically. So that's what the other package does.
Okay. Cool. So are they configured to read the same exact JSON input?
Yes.
Okay.
Indeed.
Cool. So I'm just about done here. Awesome. Okay, so let's see here. All right, I'm going to switch back over. So in this benchmarks directory, this is the implementation, correct? The implementation of in Parsica.
And it's using the PHP bench package, like the benchmark package.
Okay. And
it should be in the composer install if I'm not mistaken.
Okay. And then JSON P, this is
this is
the version that came from the JSON API spec.
No, so this is the declarative part. Sorry, this is the traditional parser, like the other package.
Okay.
And then the Parsica implementation is in the. If you go to the source, yeah, it uses
I see. I see.
Yeah,
Okay.
Parsica JSON.
Okay.
Thing.
Okay, cool. All right. So I think the first thing we're going to do is just try to run this and make sure that everything runs correctly. So let's go ahead and run. Okay. Would we have expected some output?
No, it should have been using the PHP bench package, and I think it's one of the composer run scripts.
All right, so let's see here.
Yeah, composer benchmark indeed. Yeah,
okay, awesome.
That's it. Okay, that's not working. It's probably because PHP bench is not in the composer dependencies itself, I guess.
Okay, let's see here. So we've got.
Yeah, it's not.
Okay. Okay. So we'll do composer require.
It's just PHP bench, I think. Yeah. Or not. There we go.
I'm wondering if it's a PHP 7 issue. No, it should work.
Maybe the master is a, yeah, maybe we should specify the version.
Yeah, so let's do...
Could not find a matching version.
Okay, here we go.
That looks good. Yeah, there we go.
Okay, cool. So what we're probably going to need to do is break some of these out into smaller pieces. Because, well, there's probably some other ways we could do this with Blackfire, but really what would be the easiest thing to do would be to have just one script that does each of these things rather than each script. So I think that'll maybe be the first thing that we can try here. Actually,
yeah, we can make we can just copy paste those into a separate PHP file. That
yep.
should work.
Let's do that. So I'm going to give you full access, and I'm going to send this to our chat in case you need to jump in.
Yeah, I think we forgot to set that up.
Yeah.
To be honest. No problem.
Well. There we go. So it appears that the chat may not actually be coming up correctly for us. So I just saw something from Oliver Davies that hasn't actually shown up on our stream yet, which means, yeah, I need to move things a little bit. Oh no, there it is. Awesome. I can see it now. So go ahead and try clicking that link to see if you can get in while I jump into our benchmarks.
Yeah.
So
I need host approval apparently.
There we go. Okay, so struct.
Yeah, I'm in.
Awesome. All right, so let's go ahead and let's tweak this by adding what's the best way to do this?
Well, I think we could just make those three functions, three different files.
Yeah.
That should work.
Okay. Let's copy them to the same name as the function names. Okay. So now we can just worry about these individual files. So the base max.
Yeah, we can just remove those two other functions, I guess.
Can you run specific benchmarks this way?
Good question. Bench. Let me look that up.
Because if we do that, it might make things a little easier. So, all right, we've already started this, so I think this is going to be fine. I think that the the other thing about the profiling is we don't really want to profile the benchmark application. So
yeah, indeed.
so
Maybe we should do it without the benchmark.
Yeah, so I think this is going to be fine. I just thought if there was a faster way to do it, we could try that. And so I think the first thing we'll do is create a baseline for each of these. So this is the Parsica. All right, so base max, JSON encode, and Parsika JSON. Okay, so these are all fine. I guess the other thing we have to do is we'll have to do one of these for each of these.
Mm-hmm. And then we can probably lose the revolutions and the iterations as well.
Yeah. All right, now let's run these. Ah.
Yeah.
I did this yesterday too. There we go.
Oh, you had a trial run?
Well, no. Yesterday when I did something with a vendor autoload, I did composer autoload. It's been a little too long since I've done this, apparently.
Ah, yeah, you mean, yeah, I understand. Yeah. The vendor directory.
I don't know why. I don't know why this one's upset.
Missing file.
Oh, okay. Okay, cool. So they all execute now, which is good. So let's go ahead and try Blackfire. So we'll do Blackfire run, and we'll try benchmarks. We'll do bench JSON encode. And so running Blackfire at this point, it sets up the appropriate headers, not headers, environment variables that the probe can detect to know, hey, we need to profile this one. So all Blackfire run is doing is setting up some environment variables. So you can call any PHP script from that point, or any script really, and it will be able to profile any PHP run in that environment. Okay, and it's going to give us our profile, which went to the wrong window, of course. Okay, so this is everything that was required to get the base JSON parser working, like the thing that was included in PHP. So there isn't going to be a lot of userland PHP stuff, and I'm guessing the built-in JSON parse, parse isn't even going to show up in here. Let's see if we can find. Okay, so there's one call to JSON decode.
Yeah, that seems good.
And we can see where it was called from, but it the amount of time spent here on CPU processing is minimal. So one of the things that Blackfire is going to do is it's not going to show you things that don't take a minimum amount of time or minimum amount of resources. So the benchmark for the basic one here is essentially not going to show us anything really.
Which is great. Then we know that we're very slow.
So we'll try the base max?
Yeah.
All right. So we'll run this one.
This one is, I think, 150 times slower than the default PHP one.
Okay.
Which is still pretty fast, actually.
Okay. So this one, we look at these two profiles. We can't really compare them because it's like apples and oranges, because they're different code paths, but we can get a general idea. They might actually look relatively similar. Okay, so there is this Json Benchmark call. So this is now using enough resources to actually register on the call graph. So we can see that it's using 1.66 milliseconds.
Yeah, about half of the time that the composer autoloads.
Yep, exactly. So what we can see from here is what are the calls from this point. So we can see that there's a call to the JPO PHP JSON decode. There's a compile call and run init. So these are where the calls are going from here. The thing that we're not really seeing a lot of is the memory. So I think memory is one of the things that you were kind of concerned about with this as well, right?
Yeah, of course. This base max one is still pretty good.
Yeah.
So if we do the same thing with Parsika, you might see the memory thing show up.
Yeah. Both the base max one memory wise seems to be reasonably close to the
other one, the native one.
All right, so let's try Parsika. And so the profiling does add a little bit of overhead. So especially if there's something that's super complicated, the profiler will make it seem a lot slower than maybe it needs to be. Oh yeah. So this is
and there we go.
This is the recursion. But I do see that it's, at least in terms of memory, it's
about double of the others.
Yeah. Okay.
Yeah. So I totally expected this, of course. But the interesting part comes here, I guess, right? Where we can dive in what happens.
Yep. So it looks like there's a closure where 91% of the time is spent. So
yeah, and seeing that it's all functional programming inspired, there will be a lot of closures here.
Yeah.
That might make things a bit more difficult to debug or something.
All right. Okay.
Okay, but they list the lines and the files where we can find them. So
I don't know if they actually list the.
It looks like it does, like in the bottom square there, the closure source combinators in the graph. I mean, yeah, they list the line number.
Okay.
192.206. I think that's the line number.
Okay.
So it looks wow.
So what's going on here? I think you were saying that it looks at each character and creates a new stack for each character. Is that right?
Yeah. So for this, we might actually want to look at the parser definition itself. So
is that what this is?
Yeah, no, that's the benchmark one. So in the source directory, you will find it under JSON. Yeah.
Okay.
So what we did is we built this parser, as I said, based on the spec on json.org. So here you can see at line 61 there, we start by saying, okay, consume white space, and in sequence with that, we will try to parse a JSON element.
Okay.
So first we consume all the white space. That WS is actually a parser. That sequence is a combinator, and then the next thing inside the sequence is of course another parser. So there we're sequencing two parsers.
Okay.
Then here the white space one is again, you see take while, which means consume characters while they fulfill this predicate. So if the character code is equal to one of these, which are spaces, tabs, new lines, then we'll just consume them and return null as the data structure that comes out of it, which is that void left.
Okay.
Output null.
Okay. So the output is null.
Yeah. So that's basically like a trim of the string.
Okay. Okay. And then sequence.
Yeah, so sequence is a parser combinator. So this actually is already quite a interesting case. So if you would click through on that, you would see that it's immediately a closure inside that sequence call there. Yeah, you can't. Yeah. So here we come into functional programming territory, right? So we use a bind, which is a monadic bind, basically, on the parser, and so it will run the first parser, and with the result of that's that function on line 142. Yeah, with the result of that, it won't do anything, and it will immediately run the second parser.
Okay.
So that's the sequence thing.
And it passes the result.
Yeah, it always so this is actually a parser definition. As you can see at line 140 at the end, we return a parser. So basically we take two parsers and we return a parser, and it actually doesn't do anything parsing yet. It's just making a definition of a parser, which is already recursive, etc., etc. So this is already quite complicated. And then with the result of this, which is the result of that JSON function here, that's actually the parser, and then we use that to pass a string to it and parse it.
So this is,
yeah, the element is basically any JSON object. So if you click through on that, you will see here that it's again a parser definition where we say it's any of these things. So an object, an array, a string literal, a number, true, false, or null, which are basically the different options you have in a JSON parser, right? As object types, and those again are implemented as separate parsers. So yeah, for instance, the true one or the false one is a good one to start looking at, or we can look at the object one. Yeah, why not? So yeah, here true is just parse a string true, and then map that to the actual PHP value true, and that's what the parser will do. So it will eat up the characters of the string true, and then map that to the actual value true in PHP. The token thing is also eating up white space at the beginning of the string. Sorry, at the end of the string. Yeah, as you can see here. So keep first. So it does the parser, and then it takes away the white space at the end.
Okay.
So yeah, just like this, you can basically in human language define the how you parse a JSON parser, right? So the string literal here is an interesting one, and I think this one is one of the reasons why it's slow, because
it's
what we
character
do
at a
here,
time.
yeah, what we do here is we say, okay, between these two characters, so the double quotes there, we say, okay, take 0 or more times the choice. Either it's satisfying this predicate, which means any character that is not a double quote or a backslash, basically eating up all the characters that are not ending our string. And if it's a backslash, we look if it's followed by one of the escaped characters in a JSON string, so that we can keep those, because we want to parse them inside of the string in that case.
Yeah. Okay. So if someone has escaped, or if someone's used a tab
T
character,
yeah,
we want to be able to
indeed.
map it to a PHP tab character.
Indeed.
Okay.
Indeed. Yeah. So, but here you see that combination of the 0 or more and the choice means that it needs to try to satisfy for the current character, see that it's not a double quote or a backslash, and then it can only go to the next iteration, and that's the next character in a string. So basically, it needs to check each character individually, and the 0 or more, if you would click through on that, is again implemented using a separate parser. So it's a parser that it's evaluating at this point in a while loop. While this parser evaluates and it's a success, go on to the next one. And that append and continue from thing is again using a bind, etc., which is again a recursive call. So yeah, this might be this might be an expensive thing to do for the memory as well, which I don't know. We can try to find out.
Okay.
So yeah, as you can see, it's made to be easy to change and to create, but it's not really built for
performance,
being very, very performant. However, I've seen libraries like this in JavaScript which are immense, like 1,000 times faster than. So I know it's possible to go faster.
Okay.
So yeah, I don't know if my explanation is clear to you or not, or should we?
Yeah, it's clear.
Okay. Should we go deeper, or should I explain a bit more?
So I think so one of the benefits of using a profiler, sometimes it's useful to be able to actually see when there's a problem. Other times where this one might actually fit into that category, it can be very difficult to actually walk through to figure out where the issues are. And what we can do instead, since you have an idea of why the performance is slow, what we could do is experiment with some potential fixes, and then look at that to see how it's impacting the actual profiling. So if you have do you have ideas for things that we could do to try to make this better?
That's a difficult question, though, because I have an idea where it might situate, but I'm not completely sure. But if that's right, and I'm also not sure what the exact fix would be.
Okay, I mean, we can try it and see if you have an idea. If not, then we can try to look around for other stuff.
Yeah. So in this case, the continue from call there. I think that one does a bind internally. No, it does a run. Okay. So it's running the next parser with the remain. Okay, yeah, that's fine actually. That's not a big deal, to be honest. The bind itself is an extra closure on top of the stack.
Okay.
So I was a bit worried that it was that, but it's not.
I was trying to, where were we at? We were in combinators. There we go. Continue from. Okay.
Yeah, 0 or more. So this might actually be fine if it's just that while loop. Of course, it's still checking one by one the characters, but I'm guessing it's also doing that in the other parser, to be honest.
Mm-hmm.
Because if you want to see that you're still inside of a double quoted string in your input, then you basically have to check every character to see if the next one is a double quoted string.
Okay, so what about the fact that this parser is already, in theory, asserting that it's between two double quotes?
Yeah, so what that between does is basically it parses that first character at line 185, and then it does the last parser. So, and then just at the end, it tries to parse that last character.
Okay.
So it's just a sequence basically. I think if you go into the implementation of between, that you will also see that it's just a sequence. Yeah. So it's keep second, which means it does the first parser there, the open, and then it rejects what it reads from that, but it eats the input and throws it away. And then it does keep first, which does exactly the same, but with the second parser that you give it. So in this case, it will keep the middle part and just it will parse two double quotes. Everything inside those double quotes will be kept. So yeah, it's just a sequence where we just throw away the first one and the last parser there. So yeah, it's not asserting anything really. It's not like in a regular expression where you can say, okay, just stop at this character. That it's not yet doing that. You have to do it yourself. Yeah, maybe the string is not the problem then. I thought it might be, but maybe not. This looks pretty.
All right, so let's take another look at this then. So for the profile, if we look at CPU time, the things that are taking the most resources, if we sort by exclusive time, might help us figure out which things are actually taking the most amount of resources. At least in this case, the time resource. Yeah. So we have string stream take is at the top of the list.
Take one.
Yeah. Oh, yeah.
That's
sorry.
The number of calls to that one is the highest.
Yep.
Okay, and the take one is basically the so we work with streams. In this case, the stream is just a string, and it's just taking one character from the stream. Basically.
So this is probably called from char.
Definitely, and also other like the take while would also do that. I guess.
Let's see, line. What was it? 31.
Yeah. Satisfy. Yeah. So there we have it at line 33 there.
Okay.
So satisfy is the basically the simplest parser. You give it a predicate, and if the character that it finds matches the predicate, it will result in a success, and if it doesn't, it's a failure, and it backtracks.
Okay.
So the parser backtracks on that failure. So I think maybe the backtracking might be a problem.
Okay.
Because 1,500 calls to this is actually a lot.
For which one?
For that take one, so 1,500 calls, I don't think our input has 1,500 characters. So if that's the case, then we're backtracking a lot and basically reading the same character over and over again, which of course, if we could not do that, would be a huge improvement.
Okay, so let's see if we can backtrack this then. So let's zoom in on take one.
Okay.
Okay. So
that's a lot of calls.
Yeah, so they're mostly coming from that same.
Yeah. Okay. So they're all coming from the satisfy call, which was that line 31, right?
Yeah, but let's see.
And then you get the huge tree. Okay.
So 380. I want to make sure this edge actually goes to where I think it does.
Okay, so that's parser PHP.
Yeah, so that's
380 12 times.
380 to 386.
Okay, that's the label. Okay. Okay, so from label.
So also, this is just one example, to be clear. It looks like there were 12 calls to take from here.
Okay, so 12 of the 1,500 calls come from here. Okay. Yeah, okay, that's fine. That's fine, I guess. And still, label is something that actually shouldn't really do anything. So I'm going to write that down actually, because labels shouldn't have an impact. It's just labeling your parser with a more understandable
output
title, so that if it fails, that you get to see instead of expected character A, that you can give it a name, expected string or something.
Okay.
So that shouldn't actually do any.
So
calls.
Whatever this parser function is, I'm guessing this is calling the take one.
Yeah. Result this parser function. Okay, it's the label implementation on the parser. And it calls the parser function input. Yeah. Oh, it's been a long time that I've been in this class. Yeah, so we have this parser object which wraps the functional implementation. So basically, our combinators, etc., are functions, but we return a parser object wrapping that function as a field.
Okay. So
that's that parser function.
So this was a good example to look at. If we look at the callers, we can see that there were 46 callers, which is why there's a nest
one
here.
One of them is a big chunk.
Yeah, so we can look at the one that has the biggest chunk. And so this is coming from run.
Okay, yeah, that's parser run. Which seems logical to me, yeah. So basically, again, that's that parser object wrapping the parser function. And so we give it some input, and if we run that parser on that input, it will produce that parse result. So I expect most of the calls indeed to come from here. That's the logical thing. Of course, that doesn't tell us anything about if we got a result success or a result failure here. And I guess the failure ones are the ones where we backtrack.
So this is interesting, actually, because the other thing on some of these you'll notice is this little at 50. And so what this is saying is that this is at the 50th level of recursion. So this wasn't just 39 milliseconds of time in run. This was 39 milliseconds of time in one specific instance of run.
Okay, that's a lot then. Yeah.
So let's see if we can zoom in on this and see what's happening below it.
Mm-hmm.
If that's a thing, there we go. So it's calling...
Wow, is that 7,000 times is success?
Yeah, is success is called 7,000 times, yeah.
Okay, nice.
I feel like it took me to the wrong spot here. So let's do run at 50. All right, so unless there were multiple calls too. Yeah, okay, so we're in the same spot. So run.
Yeah, so we have run at 50, and it has also a big chunk of callees then, which is like almost the same size as the big chunk in the callers.
So this big chunk here.
Is that combinators? Yeah, that one, line 192 there. Okay, interesting. Okay, that's an either. Yeah, this is actually exactly what I thought. So either is like a choice between two parsers.
So it's running the first parser, and if it fails, it runs the second, which means this could potentially be a waste.
Indeed, indeed. And we backtrack, and then we do the second one, starting at the same point in the input. As you can see, 195 and 199, we use the same input variable. So it's actually like backtracking, right? It's taking a copy. So it needs to keep that all in memory. Of course, everything is immutable in Parsika string stream right now. So we're constantly taking copies of the input. So I guess for every character that we read, we're just copying the whole string without like -1 character or something. So that might be a memory thing then. But the memory seemed quite okay, no?
Yeah. I'm wondering if it would be... well, you know what? Let's look at the timeline before we do anything else.
Oh, wow.
All right, so we sort of expected.
How do we?
We sort of expected this.
How do we interpret this?
So the blue background represents memory consumption.
Okay.
So it doesn't really look like memory consumption is a huge issue here. Like, it's not like there's a spike anywhere. It peaks at like, well, I guess. So yeah, so it peaks right here. This is the last big jump where it tries to parse a string.
Okay.
After that, memory jumps up just a little bit over time. So this looks really healthy to me.
Yeah. So everything before that is building the parser?
Everything before this is yeah, so this is like Composer right here.
Okay.
Yeah, so this is Composer, and then this is the point where we actually call into Json Bench.
That file.
So this is right.
That's the clause that we copy pasted, probably.
Yeah, so that's right here, and so there is a bunch of time there before it even tries the string. So I'm guessing this call to JSON building the parser.
That's creating that parser.
Yeah, that's actually taking a sizable amount of time, isn't it?
Yeah, indeed.
I mean, it's still only a fraction of what we're looking at overall, but this does seem to surprise me a bit. I mean, it's still only 7 milliseconds, I guess.
Yeah, the thing is, of course, it builds a complete tree, recursive tree of parsers, which, indeed, I expect it to be a bit slower than in the other case where it's just a procedural code, because it first has to build that whole parser. Yeah, so basically from within object, it will refer back to element.
Okay.
As you can see, JSON member there, 102, is in turn referring back to element. So yeah, I don't know how PHP handles like recursive data structures, to be honest, in memory. But I think that indeed might be a little bit of a problem with the time there, right?
Yeah. I mean, when would it stop?
I think it's so we that recursive method that you were in before is basically, okay, so we create that parser object, we create an instance of it, and then we say, okay, it's recursive, which means that it will just take the variable that we assigned it to and recurse on itself. So it's basically just creating a recursive data structure. But if you would var dump that structure, it would never stop. PHP would tell you that it's a recursion. Like you get this star recursion abbreviations in the var dump. Of course, that's because the definition of a JSON parser, by definition, is a recursive parser. So
yeah, I guess I'm having a hard time understanding where the work is involved here.
Yeah, so there's two steps. The first step is building the whole parser, and then the second step is the parsing itself, which is the try string. You can see it in that bench Parsika JSON.
Right. But so, I mean, at this step of creating the parser, I mean, it's white space. Like, none of these functions that we've looked at so far seem to be super.
No, indeed. So this is just basically building that data structure of parser elements,
Right.
parser instances, which is just a data structure, right? So it's building a data structure. It's like 20 elements and then a recursion on itself, something like that.
So I guess that's where I'm wondering, where does that recursion stop? Because
it doesn't. Yeah, so as you can see here, we say element is recursive, and then element recurs on itself, and then we return that element. So basically, if you now call this method element, you will get a data structure that's already recursive. Yeah, it's a bit hard to explain without looking at that recursive call itself.
So this isn't calling this now. This is actually a callback.
Well, yeah, indeed.
Okay.
It will be called when we need it.
But this actually calls JSON member.
Yeah.
Right now.
And in JSON, indeed, and in that member,
it calls JSON element again.
Yep. And in element we have that
object.
If not is set, which is static, right? So if it's already there,
my bad.
We will immediately return that recursive element there.
Okay. I was missing that part. All right.
Okay. So you mean with where does it stop? You meant here, right? If the if makes it stop,
yep,
and immediately returns itself, but the data structure itself is completely endlessly recursing. But
right.
it's just it stops here. Indeed, the evaluation stops here. Yeah.
All right. So let's see if we can look.
And that's all happening in that first few milliseconds, indeed.
Right.
Okay, and then the parser try string there is where we actually start parsing the string, and you as you can see, it immediately dives down into some calls. Oh, here you can actually really nicely see how long they all take. So it increases the stack like every time with 10 levels. This is interesting.
So what I'm noticing is that there's
one distinctively taking a lot of time there.
Yeah, it seems like there's a few of like it dives into the stack a few times and eventually hits something that takes a little bit longer. But each of these little bit longers really start to add up.
Yeah, indeed, and I already saw that a few of them are the same ones, like the 223 and the 112.
So 112 was up there also.
Yeah, indeed. Yeah.
Okay.
And here is the other one again.
So let's go to.
Okay, that's append. Yeah, of course. What does it do? It runs the first parser, and it runs the second parser, and it gets two parse results, and it uses the append method on those parse results to append the results. For instance, this could be any data structure that you decided that the parser should have parsed, or a string, for instance, or two arrays. And then the append method would append them together. And I don't know what they're appending at that point, but I don't think appending strings takes a long time. Appending arrays does. Maybe can you click true on the append?
This one?
Call? Yeah. Okay, there is an implementation. It's probably in the success implementation. Succeed, yeah, that's that one. Sorry. Okay. Append success, yes.
I have a question.
Yeah.
Is fail calculated every time? Or is that memoized?
I don't think so. It's just the type of the
I'm sorry about that. I keep getting lost here. Okay, so here we go.
Yeah, so if you click through on isFail, you will see it. Again, it's an implementation with the green arrow on the left. You can. So in this case, if it's actually a failure, then it would just do okay. The opposite of this is success, and a success is just hard coded to false.
Okay.
In this case, and for succeed, it will be
the opposite.
The exact same. Yeah, the opposite indeed. Yeah.
So append success.
Yeah. Okay, and this is a bit ugly because we had to hard code some stuff. We don't know what the result of a parser will be in Parsika itself. So we need to do some assumptions here. Basically, if we get null, we can just take the remainder of the other results. If we get 2 times null, yeah, it's null. If the types are not the same, then yeah, this is impossible to do. And then if the types are a string, okay, we know how to append strings. It's just with the dot operator there at line 121.
Okay.
If it's an array, we do an array merge, and this is what I'm expecting to be slow.
Okay.
Like for all the JSON objects and arrays. But I don't know actually. Is the dot operator something slow? I wouldn't think so, but
yeah, I wouldn't think so either. All right, so let's see what we can actually. So we looked at two.
At that array merge, basically we could look for calls to array merge probably in Blackfire then.
Yeah, this view is really heavy.
Ooh.
Okay, so there aren't a lot of calls to array
okay.
merge.
That's good. So then why are we spending all this time here? Is it because we okay. Yeah, so let's say we have two parsers. They both parse one character each, and we do this append success thing with two parse results, which are one character. That means we create a whole new succeed at line 121 again. We create a whole new succeed instance for just appending two characters. So that I don't know how heavy that is, creating new class instances. And then we still have the remainder there, which also needs to be copied over, etc. Yeah, there you see it, huh? Yeah. So I expect this to happen for every character in our input string at least. Um, but again, I don't think the input string is 3,000 characters though. So also for the combinators, it should make succeeds, but still 3,400 is a lot.
So they're inside primitives. It's calling it almost 1,400 times.
Okay.
And inside append success, it's calling it.
Yeah. So that append success is so that's to be expected. But the other one is a bit suspicious, maybe. Primitives.
I mean, these are
31.
also only 4 milliseconds total
Oh
time.
wow. Okay. Well, yeah, 4 milliseconds, of course, is 1,000 times more time than the
Yeah.
the complete native JSON parser.
Yep.
Or is it 100 times? No, I might be wrong. I might be wrong.
So I might want to try something here. So we did 223. So we know this is one spot. The other one was, I think, 121 or 112.
Yeah. In the same file. Okay.
So this isn't apply.
That's a bit harder to explain. So let me think.
Well, I guess we don't have to. You don't have to explain it necessarily if we know what it. If you know what it does or is.
Yeah, it's basically a functional concept, an applicative, which is happening here.
Or I guess what I mean is, if it looks like it's doing what it's supposed to, then that's okay. If there's nothing that jumps out at you that looks like it could be wrong.
So what it does is it parses. So it uses the first parser that you give it to parse the input. If that fails, it's immediately a fail. And if not, we expect the output of that first parser to be callable, and then we continue parsing on the remainder of what we parsed at first, and then on the result of that second parser we apply that callable.
Okay.
So yeah, hard to explain to you right now why we need it, but we do need it.
Yeah, I just wanted to make sure there wasn't anything jumping out here, because these calls are the things that are taking a long time. Between these two, something inside here is taking a while.
Okay. And can we then zoom in on that?
We could probably go to the other view.
So it's source combinators 121, 112. Yeah. Okay, and that's one big chunk there. It's the continue with thing. Okay. Continue with. Takes the remainder, I guess, and then runs another parser. Yeah, it's hard to know
Hmm.
because it's such a deep stack. Uh, like I'm pretty sure that the continue with then does 1,000 small things as well, and yeah.
So so 112. Let's go back here again. So that means one of these. This is getting called, right?
Okay.
So let's
Continue.
do.
Okay, and that one also has one big uh, callee. And that is run, yeah. And then yeah, the whole thing here is also recursive. That's run is again like the top of the we're back at the top then because it's again the parser run
Right, the
there.
main run.
Yeah. So hard to know actually where the it's probably like death by 1,000 paper cuts or something because we're doing so much um, growing of the stack and doing a few little operations and then growing the stack some more. But indeed, here you can definitely see that it's always like the growing the stack doesn't take a lot of time.
Yeah.
That's what surprises me actually.
Hmm. Yeah, it surprises me too that there's not like what's going on in here.
Yeah. That's the question. The thing is, of course, the next thing is always the succeed continue with.
Hmm.
I might be wrong, but I saw that a lot of times that it's the first thing that we do
Yep.
afterwards. So does it take that long for matching a single character? Is it possible to see that flame chart like uh, without the zoomed in thing?
I think we could maybe zoom in or zoom out a bit. Yeah, so the succeed with or succeed continue with, those are taking a lot of inclusive time, but they
Mhm.
aren't doing a lot of exclusive time.
Okay. Oh yeah, that's good. Okay, so it is what's below them that's taking the
Yeah,
time
so it's run.
to run, and then again probably what's below run because run itself also doesn't do anything.
Yeah. Well, um, run appears to be taking exclusive time here.
Okay, 200 milliseconds. Huh. Okay,
240.
that's interesting.
I wonder if there's something wrong with this output, though. Here's 239. 70.
Yeah. Okay.
So this is
Of
at the
course, run.
59th level of recursion. So I'm guessing run continually gets smaller.
Yeah, indeed,
Like the
indeed.
deeper it is in the stack, the less time it takes.
Mm-hmm. So yeah, that's why I asked if we could zoom out on that flame chart. I guess the times go smaller the lower you go. Uh, yeah, yeah.
Oh, unfortunately, the
It's too big.
yeah. I might be able to.
Yeah, using the browser zoom. Wow. Okay.
What would be interesting? We look back at the examples to see if it matches the shape. It kind of does.
Yeah. You're right.
So this is all the text. Oh, it's this array.
Yeah, it's an array indeed. Yeah.
So there might be something weird in the array because look at this. This one's flat.
Yeah, and that's the string.
That's these two.
The long, like a lot more text is actually pretty long.
Mm-hmm.
So I think, yeah, you're so right. Okay, that's interesting.
So maybe there's something in the array handling.
Yeah.
Where would we look for that?
In JSON there, yeah. And then the JSON array thing. Okay, so what we do is between square brackets, we look for a parser that is a character. Okay, separated by a parser comma, we take JSON elements. So sap by will then return a list of JSON elements, which can be anything. So this is again a recursive thing, of course. Yeah, that might immediately explain then.
Should it actually be recursing?
Yeah, because it could be any JSON element, like something in that array.
Right.
Could be any JSON element. But the sap by should probably not be recursing, and maybe that's what's happening. So it's either separated by at least one, or it's an empty list is what that means. So we'll have to look into sap by one then to know what it does. And what it does is again an array merge here, by the way.
What's that?
There is again an array merge here. So basically what it parses will be a prepended to an array using that prepend function there. And here is where the apply, here we call that apply thing that we saw earlier. We call it twice. So basically the pure creates a parser with that prepend function in it. And that prepend function is a curried array merge of two things, an element and an array. And it creates then a singleton array, and it prepends it to the second array. Yeah, I guess this could be better. That apply here. So the prepend is we manually curried that function, right? So it's actually a function that takes two things, but we created a curried function which takes only the $x there. Then we pass that through to a next function which takes the second parameter. And only then, if we got both of them, we will evaluate the array merge. And of course, that works together greatly with that apply. But as we saw, that apply also does some tricks. And then again, there's a many in there. And many is probably also calling followed by. So that's again a lot of recursive calls. Yeah. Okay, so I think the problem lies here indeed with that many in combination with those others. Can we see if it's the many or if it's the apply? That would be helpful.
Um, yeah. Too far.
Um, yeah, I think it's just many as a function.
Oh, yeah.
We seem to have 5
Yeah.
watchers on the cool.
Yes, indeed.
Six even.
I sent a chat message earlier.
Cool. Hi all. Nice that you're watching us.
All right. So let's look at apply again. Apply is not showing up anywhere here.
Okay, so it's probably the many call then. That
Nope.
also not showing up. Huh. Yeah.
So we were here. We were looking at.
Yeah. So the sep by. So separated by the character parser comma, we have the parser element many times.
What does token do?
That's the eating white space of the end of the wrapped parser. So in this case, if you parse the comma, it will then eat all the white space after the comma.
Okay.
So yeah, that's the keep first, right? Keep first, and we passed a comma to it, so it will keep that comma, and then it will remove the white space. Member is that's not the right one yet. That's a member of an object. Yeah. Array, there we go. Yeah.
So
Now I'm
just to be clear, it makes sense to you that this should be recursing for each element in the array.
It makes sense that it does. I don't know if it should.
Okay.
It makes sense in the way that everything currently works using recursive functions and passing functions and that kind of stuff.
No, I think that makes that makes sense. But I guess what I'm getting at is by the time it gets here, there's like a baseline. There's a baseline level, right, that these things return to when they're finished.
Yes, indeed. Yeah.
None of them ever get this high.
Yeah, you're saying that staying closer to that baseline might be beneficial.
Well, I'm just wondering if this is an indication of something going wrong.
Yeah, and I think it is.
Yeah.
I think you're right there.
Especially if there's like any of the backtracking stuff that you've talked about. Like the further in it goes, the further it has to backtrack.
Yeah, but in at that point, we're already parsing an array, and we just looked at the sep by, and in the sep by, it doesn't have to backtrack as long as the array is valid, and we know our input is valid. So I don't think it's the backtracking there per se. What surprises me is that like the string doesn't go as deep as the array, to be honest. I that surprises me. Of course, there we probably do a take while. Yes, we did a take while. Probably if that string was a string full of escaped characters, then it would probably also grow the stack way more than it does right now. But because we have in the string implementation, we have a take while, which is an optimization.
Wow, that
if
is
you
a
would
really long string.
Yeah. So if you would add like the same length of string, but just with tab characters, for instance, on a new line or something, and then if we would parse that, I guess that would tabs or something. Yeah. Yeah, I yeah, I just copy pasted some lorem ipsum stuff in there.
Hey, Oliver Davies. Hey, Madison. All right, let's see if we can jump in here.
Getting some pressure on it with some more viewers. Okay, you see, it's already a bit deeper than its string thing. Not as deep as I thought it would be. Okay.
But we could definitely see.
Yeah.
That we've added something new.
It takes less time than I thought it would, that one. Okay.
So
the array is still a bigger problem than that. Of course, it's an array full of strings. Maybe what if we would do an array full of just true, which I think true and false are very easy to parse.
I guess I better keep them as close to the other style as possible. Then I'll do false, and I'm going to do a whole lot more false.
I guess with Command D or something, you can just duplicate the whole line.
I don't know that one yet. All right.
Yeah. Now we have missing commas, of course.
Oh, you're right. Awesome.
A few more. Yeah. Okay. If that's as heavy as that string array, then we can exclude some more stuff.
Yeah, thanks for pointing that out, Oliver. Oliver just told me line 65 in chat. Let's see what we got now. Oh, interesting. It does not like this. I think we broke something.
Oops.
I use the term broke something very loosely.
Well, it looks yeah, they're around 300 milliseconds there. It's again going very deep. So that might be the...
Yeah. So it took this long to be able to scroll smoothly.
It's okay. It's even bigger than the first one.
Yeah.
Okay. Okay, so definitely there. That's quite bad. Basically, one extra element in the array grows our stack by 10 or something.
Yeah.
Or more.
Wow. Yeah, these are actually the same. So this is the cost of an element.
Mm-hmm.
Since they roll back to the same outer level.
Yeah, indeed.
So if we focused on this section right here to look at all of the things that happen at that point, we might be able to find something in there that would...
Yeah.
Yeah, that's one of the cool things about the timeline with Blackfire, or like, the profiling tools. They like seeing patterns is the fun part.
Yeah. But it was good to look at this because the other graph there, it shows the connections really nicely, but in this code base with all the recursion, it's actually a bit chaotic.
So there is a difference here. Right at this point, these two trees are different. Like between here and here. Okay. So there's some difference that happens right at this point between these two.
Yeah, of course. One of them is parsing strings, and the other one is parsing the Boolean false, right?
So then
and that Boolean false thing is actually a lot simpler.
Okay, but the interesting thing is that by this point they're in sync again.
Okay, that's weird too.
And then they stay the same 16. All the way up to...
Okay, and what's different?
What's that?
What's the different part then?
Hold on. Yeah. I don't know if they've done a lot of work with this much recursion. The browser kind of struggles every once in a while here.
Yeah, it's potential. So we're probably rendering lots of diffs.
Yeah. You can kind of see the browser triggering the... You've scrolled down, but I don't know what to do with that.
Okay, there we go.
Yeah. Okay, so this is...
That's still the same.
Yeah. This one
still looks the same.
It's here. Nope. Here.
Okay. Continue with 11. Parser run 66. Parser combinators run. This actually looks still the same to me, or largely the same.
Yeah, so
Okay, there we have two closures at the... Okay. There's that 112 again, and 223 at the left. So those were the continue with, and what was the other one? I forgot. Yeah. 23. I'm just saying random numbers.
yeah.
Yeah, that looks different there. We have parser run 59, parser run 60, parser run 61. Really fast succession there on the right.
So it looks like they aren't, maybe at this point right here, parser run 58. They're at least in sync with the parser run call. And then all the way up until here, they're subtly different.
Yeah, it starts to get back in sync after a succeed, continue with, and before that, that's probably backtracking though. Oh, I can think of something. Since false is one of the last things we try in the member, JSON member, it will first try all the other JSON structures first, and it fails until it comes there, and then it succeeds. Yeah. Of course, we can make this faster, but then it will be slower for other elements.
Yeah, if it turns out that's what caused that, yeah, definitely.
Yeah, it looks like that is what's happening there. So that's not something we can really fix, but the growing the stack. Of course, we should look at the indents there in that graph, right? Yeah, that will be, yeah, that will probably oops. I know that was a git change, probably that red thing. I thought it was a failure of the script.
It doesn't look like it actually. It may have cleaned up, or that may be why it was off in the beginning. But it's still just as long.
Okay, but now it's not doing that. Or it is. Yeah, it is. Huh. Actually, what I see here is that the indents, like, or so it means the time it takes on the right side is much shorter than on the left side in this case to go deeper.
Yeah.
Right, so it goes deeper in less time. So that's probably the parsing of the false that's faster than parsing of the string inside the array. Yeah, it looks like the combination of that array together with parsing those strings. what conclusions do we make from this? Well, it's definitely interesting to see what it does here with the stack and with the timing, just from that simple definition of the array. Like it is easy to understand, but it's really bad for the
Yeah.
performance apparently. And as you can see here, it's always just a little bit of time, like a few milliseconds, and then we grow the stack with like 10, and then a few milliseconds. So it's always just that parsing that one string. It takes a long time combined with the other strings in that array. It's not like individually they take a lot of time.
Yeah, so if this is actually the time it's taking to parse the string versus...
Yeah, that's what I'm thinking right now, like that little indent there.
So that's string literal. We looked at this one already, right?
Yeah. Yeah, indeed. So if that's the case, then this is pretty fast. But of course, if you do it a lot of times.
So I have a question.
Yeah, go ahead.
Why would this be here?
Okay, so
because it's possible for this case?
No, it is there because otherwise we would start parsing. How should I explain? In regular expressions, you have the eager and non-eager star, right? And if you would say parse a double quote in a regular expression, and then dot star, and then parse another quote, it would parse that double quote at the end with the dot star because it's eager. And here the 0 or more that we use at line 187 there keeps on trying that choice, and satisfy in this case takes any character that is not in that array. So that means it eagerly will eat anything that's not in that array, and to make it not eat that last double quote, we need to say, okay, yeah, you can't parse that double quote here. So that's why that is there. And then so that means we stop before we take the double quote at the end of the string.
Okay.
And then at line 186, we have defined that the last character that we want to parse is the double quote. So I don't know if that's clear.
It is, but if we don't want to parse it, I'm wondering why we need both of these.
So we want to parse it, but we don't want to have it in the body of the string.
So this isn't just for the last one. This is also for the first one as well. This will eat both of these.
No. So the between is basically a sequence of that first 185 character parser. So that one already eats that first double quote. And then it uses that 0 or more to parse everything in between up until the next double quote. And then it uses the parser at line 186 to parse that last quote. But the body of the string doesn't parse any double quotes.
Okay.
Except for an escaped one, which is at line 192. and that's of course because of the choice parser. If it doesn't satisfy that first parser, we go into that second one.
Can you help me understand the difference between token char and what we have in string literal where it's not doing token?
Yeah. So the
it's doing
token
JSON
part,
token here.
yeah. So it basically will parse your string, including the double quotes at the beginning and the end, and then it will also parse trailing white space, and that trailing white space will just be neglected, or it will be eaten, but it's not showing up in the result of the parse. Um, so it's gone at that point because it doesn't have any meaning in JSON, right?
Right.
You can just add new lines and white spaces where you want.
Okay.
So that's the token, basically stripping trailing white space.
Okay. Okay, I get it.
Cool.
So I think I need to be done with the stream here pretty soon.
Yeah.
Hey Ramses, nice to see you. I think that
well, actually, first of all, thank you
sure.
for taking the time. The I think I learned the most from you showing me how to do this Blackfire thing. I think I'm going to try it as well. And actually, the flame chart here is really interesting, or the timeline, because I now have an idea where to go look, I think.
Cool.
Not a way yet to solve it, but that wasn't the point.
Yeah, it at least gives you, like, you know where these little cliffs are.
Yeah, indeed. And I didn't know it was this bad, actually. Like for each item in that array, we literally grow the stack with 10 to 15 calls. So that's interesting.
Yeah, and you said you're aware of some JavaScript parsers that are good also, and
yeah, so maybe going to have to look at those to see how they do it.
Yeah, and you can look at specifically these issues. So you don't have to look at the whole thing and learn the whole library. You could just look and say, okay, how are they handling arrays, or how are they handling string literals, or something along those lines.
Yeah, indeed.
Cool. Awesome. Well, thanks for your time. Thanks for everyone who joined. That Ramses, my bad, you're just arriving now, but I think we're probably done. Yeah, maybe what might be interesting is if you work on this some more, Toon, if you get to a point where you've made a change and you feel like it's better, it might be kind of fun to do a follow-up one of these so that we can see see how it actually changed.
Yeah, great. I would be
cool.
Up for that.
Awesome. Well, thanks everyone for tuning in, and yeah, we'll try to get back to this at some point again later. All right, have a good day. Bye.
Bye.